Refraction of light by a glass prism. There are several glass prisms, including rectangular and the triangular glass prism. But we concentrate on the rectangular glass prism. Rectangular glass prism, this is a three-dimensional box-like shape with 60 faces, with 60 flat faces. This is the phase 1, phase 2, phase 3, phase 4, phase 5, phase 6. It is just like a book, just like a book. It's a rectangular like this one. With two opposite faces are equal. The movement of light through the glass is a straight line. Through the glass, inside the glass is a straight line. As you know that the light always travels in a straight line. So at the point of intersection between the two boundaries, between the boundary of two mediums, in case of this one, medium here is air, and this is another medium. So whenever the light passing from air to the glass, at the point of intersection between the glass and the air, the bending occurs. Inside the glass, motion of the light is a straight line. This can be observed practically. And away from the glass, the motion is a straight line, but at the point of intersection, the bending occurs. So the bending of light at the boundary of two optical densities, of two different optical densities, that is a refraction. So we have two laws of refraction. Two laws of refraction. First law and the second law. The first law says that the incident ray, the refracted ray, and the normal all lie on the same plane. The incident ray and the refracted ray and the normal all lie on the same plane. A normal, which is the normal? The normal is an imaginary line perpendicular to the plane, which makes an angle 90 with the plane. This is a normal line. Another law says that there is the sine of an angle of incidence dividing this to the sine of an angle of refraction, which is equal to constant, is equal to constant. The sine I to the sine R, the ratio of sine I to the sine R is equal to constant. So the ratio of sine I to the sine R for, for a particular material, for a particular material, the ratio of sine I to the sine R is equal to constant. For a particular material, the ratio of sine I to the sine R is equal to constant. This is known as the Snell's law. Why we are studying the particular material? Every material has its own refractive index. So the refractive index of a material, refractive index of a material, refractive index of a material, refractive index of a material. This is the ratio between the angle of incidence to the angle of refraction. Or is a number that shows how much light wave slows down and bends when it enters the medium. The refractive index of a material is denoted as a symbol theta. So theta is equal to sine I to the sine R. Refractive index of a material also can be obtained by taking the speed, ratio of the speeds, the speed of light in the vacuum or air to the speed of light in the medium. But do you note that when we take the speed of light in the vacuum or air to the speed of light in that medium, that is known as the absolute refractive index or actual refractive index of that medium or that material. Suppose the refractive index of water, if you need to find the refractive index of water, you just take the speed of light in air dividing by the speed of light in that water. It is the refractive index of water. Or refractive index of glass, just take the speed of light in the air to the speed of light in that glass. That is the absolute refractive index of a glass. For the case of glass, is equal to 1.5. Refractive index with no unit, since it is a ratio. And for the case of water is 1.33. And the others, you can determine the refractive index of diamond, glycerin, and etc. Also, the ratio between the two refractive indices, except air or vacuum, this is known as a relative refractive index. So, for example, the refractive index of glass divided by the refractive index of water, this is the relative refractive index. So any material has its own refractive index. That's why the Snell's law says that for a particular material, the ratio of sin I to the sin R is equal to constant. The refractive index depends on the wavelength or color of the wave or light. Since that different colors have its own wavelength, it does not depend on the physical size, intensity, or angle of incident. Relationship between refractive index, the speed speed of light, and the sine of an angle. Let us take theta 1 this to be the refractive index of water, while its speed should be equal to V2, V1. The refractive index of the glass to be equal to theta 2, while its speed to be V2. So since the refractive index is equal to the speed of light in air to the speed of light in the material, that material is water now. So C over V1 is equal to theta 1, which makes that C is equal to theta 1 V1. That is the speed of light is equal to, in air, is equal to refractive index in the water, and the speed multiplying by that the speed of light in the water. For the case of the glass, the results could be the same. The speed of light is equal to the refractive index in glass times the speed of light in a glass. Since both are the speed of light, so we can equate the two equations, equation 1 and equation 2. So this gives us theta 1 V1 is equal to theta 2 V2. So this relationship you can find, you can use it to find either of the unknown value. For example, you are looking for the theta 1 or theta 2 or V1 or V2. You can use that formula to find out. Also, you can rearrange in terms of ratios. So it could be theta 2 divided by theta 1, which is equal to V1 over V2. The ratio also can be related as with the ratio of the signs. So theta 1 with theta 2 divided by theta 1 can be equal to sin I over sin R. So on rearrangement, theta 1 sin I is equal to theta 2 sin R. Theta 1 means the refractive index for the first medium. Sin I, this is the sine of an angle of incidence, while theta 2, the refractive index of the medium 2. R, sin R, this is the sine of an angle of refraction. Also, you can use this to find either of the unknown value. If you need to find the sin I, or you need to find of an angle, or you need to find the refractive index of either medium, you can use this formula. Also, by applying the law of reversibility, the refractive index from glass to air is equal to the refractive index from air to glass. Reciprocal of the refractive index from air to glass. Refractive index from glass to air is equal to the reciprocal of the refractive index of the from air to glass. It is also can be used to find the refractive index. Refractive index also can be obtained by checking the real depth to the apparent depth. This is another formula you can use to find the refractive index or either of the unknown value. Suppose this is a fish there, but when you look through, the fish appears at this height. So this is an apparent depth, while this is the real depth. So the real depth to the apparent depth gives you the refractive index. For example, a ray of light is incident on air glass boundary as shown below. If the refractive index is 1.5, find the I. I here is an angle of incidence. So by using the formula, sin I over sin R is equal to refractive index. So sin I is equal to multiplication for the refractive index and the sin R. So then I is the sin inverse of that. So angle of incidence here is equal to 48.6 degrees. Also, you can use the formula to find the speed, to find the refractive index or either the speed by using the equation for the speeds. For example, water has an index of refraction of 1.33. The speed of light in air is 3 times 10 power 6 meter per second. Calculate the speed of light in water. So here you can use the ratio of the speeds. The speed of light in air to the speed of light in water. So the refractive, for the given refractive index. So then the result is equal to 2.26 times 10 power 80 meter per second. As you can see, the speed of light in water is less than the speed of light in air. Means that the light slows down and bends when it enters that medium. Another, you can use the formula for the real depth and the apparent depth. For example, a coin at the bottom of the jar of glycerin appear to be 13.2 centimeter below the surface of the glycerin. Calculate the height of the column of the glycerin in the jar, given that the refractive index of the glycerin is 1.47. So in this case, we are given the refractive index. Also, we are given the apparent depth. So the real depth to the apparent depth is equal to the refractive index. By using the relationship, the refractive index can be equal to 19.4 centimeter. Uses of the refractive index. The refractive index is used to determine in designing the lenses for glasses. As you can see here, my glass here, the optical focusing power of this lens have been determined by using the refractive index, and the cameras also they are using lenses. So generally, the focusing power of a lens can be determined by the refractive index of a material. Also, it is used in testing liquid purity and sugar levels in foods. Also used in identifying gemstones in mineral industries and improving microscope image clarity. Okay, thank you for watching. Don't forget to subscribe, share, and comment.